Let's take a look at the end behavior of this particular function, f of x equals x squared minus 1 over 3x plus 2. Now, if you go back to your pre-calculus days, they will say, well, gosh, in the extremes, these don't have any effect, so really all you have is this will cancel out, and you get x over 3. And actually, that is true. However, we want to use calculus to prove why that's true and not just simply wave our hands like we quite frankly had to back in pre-calculus. So first thing I want to do is I want to take a look at the limit as x goes to infinity of x squared minus 1 over 3x plus 2. Now, what I'm going to do is I'm going to multiply this by 1 over x over 1 over x. It's the largest power in the denominator. And that's going to give me the limit as x goes to infinity of x squared over x minus 1 over x over 3x over x plus 2 over x. Now, see, this will cancel with that x. That stays. This will cancel with that x. That stays. So this is actually equal to the limit as x goes to infinity of x minus 1 over x over 3 plus 2 over x. Now, what's going to happen in the limit here, this particular piece will go to 0. This particular piece will go to 0. And this x will go to infinity. So this limit will be infinite. This limit is actually infinite. In the extremes, this will actually look like, or at least kind of like, f of x equals x over 3. But x over 3 is not actually the oblique asymptote. Horizontal asymptotes are what we approach horizontally as we go out to infinity in either direction. An oblique asymptote would be if I have a function like y equals x, and in the extremes the function approaches, asymptotically approaches that line. That would be the oblique asymptote. But this is not actually the oblique asymptote. If I want the oblique asymptote, then I need to do a slightly another technique, which I'll show you in just a second. But likewise, I'm going to take a look here at the limit as x goes to negative infinity of x squared minus 1 over 3x plus 2. And all this work is going to be the same. So it's going to be dot, dot, dot. Everything here is going to be the same. And what's going to happen in the limit is I'm going to end up with something that looks like x over 3. But x goes to negative infinity, so the numerator is negative. This will end up giving me negative infinity. So as x goes to positive infinity, the function goes to infinity. As x goes to negative infinity, the function goes to negative infinity. So let's take a look and see if we can figure out what that oblique asymptote is. In order to do that, we actually need to use long division. So what I'm going to do is I'm going to take 3x plus 2, that's my denominator, and I'm going to divide it into x squared minus 1. Now x goes into x squared, 3x goes into x squared, x over 3 times. If I multiply through, I'm going to end up with x squared plus 2x over 3. And then I'm going to subtract this. This will go away. And then I'm going to end up with a negative 2x over 3 minus 1. And then 3x goes into negative 2x over 3, negative 2 over 9 times. If you try and figure out where I get that from, I'll just take negative 2x over 3. I'm going to divide it by 3x. That's the same as negative 2x over 3 times 3x. The x is a cancel, and that's going to give me negative 2/9. So this would be negative 2/9 times. So when I multiply this through, I will get a negative 2x over 3 times the 2, which is going to be negative 4/9. And now when I subtract this, I'm kind of losing room here, but this will go away, and I'm going to end up with negative 5/9. So this is my remainder. So this function will be minus 5/9 over 3x plus 2. So x squared minus 1 over 3x plus 2 is the same as this. So I want to take the limit of this now. So what I need is the limit as x goes to infinity of, that was x over 3 minus 2/9 minus 5/9 over 3x plus 2. Well, in the limit, this piece will go to 0, and then what I am actually left with is this, and this is my oblique asymptote. Likewise, if I go to negative infinity, I get a similar situation. So I'm going to go ahead and plot a couple of functions. So I'm going to do plot. I'm going to do my original function, which I need to spell plot right, sorry, plot. I need to do my original function, so I need parentheses to tell what's in the numerator, and that was x squared minus 1 divided by 3x plus 2. That's the first function. And then I want to do just x over 3. You know what? I'm going to do just that for right now. So I need a square bracket here so I can plot multiple functions. And then I'm going to do x equals negative 10 to 10, y equals negative 10 to 10. And let's just do thickness equals 3, so it's nice and thick so we can see it easily. And that's a good place to start, negative 10 to 10. So let's just see what happens. Okay, this looks really quite impressive, actually. Make this bigger. It looks like it is going to approach x over 3. It kind of looks like it. Well, let's take this out a little bit farther. Let's take x out to, let's just go positive for a minute. So let's go to like 20 and see what that does. Now there's a good gap there. It looks like I'm not catching up on this gap. So let's go out to like 30 and see what happens. Yeah, it still looks like I'm not catching up on this gap. So let's add another function in here. Let's add my x over 3. And that was, what was it, minus 5/9? Yeah, minus 2/9. Minus 2/9. So now I'm going to have that third function in there. So now if I graph it, now see this third function is like orange and it's right over top of it. So definitely the oblique asymptote is going to be x over 3 minus 2/9. It's going to approach this function. Either way, it goes to positive infinity and negative infinity. I'm going to go ahead and kill this function very quickly here just for a moment. Comma back, and let's take a look at it again. And you can see very, very rapidly these things converge and they look like they're exactly the same line.